Okay, before I start, let me just say how deeply honored I feel to receive this award and to, be among other people. I mean, this is the first time I've ever received an award like this. This is the first time I'm standing in front of people who aren't mathematicians or math students. So you'll have to forgive me if it's a little rough around the edges. Okay, so thank you very much for being here. And now a short presentation about mathematics. And as with, I think, all math talks, even for mathematicians, the expectation is, as a mathematician in a math talk, you understand the beginning and you're lost at the end. So if you're lost at the end, you're just like a mathematician. Okay, so I'm going to talk about how many high-dimensional spaces are there. And before we can talk about high-dimensional spaces, we have to talk a bit about spaces. So the space you're probably most familiar with is Earth. We live on the surface of Earth, and the surface of Earth is a space. You can walk around on it, you can measure distance on it. Now, this representation of Earth is not particularly accurate. I'm sure you're much more familiar with this one. So as you know, if you keep walking north, eventually you wrap around and you end up at the bottom again, right? So this is another space. It's a donut. It's a slightly different space. If a donut can have one hole, a donut can have two holes. There's another example of a space. And maybe a rough definition of a space for tonight will be something like a space is an object that has points and where you can measure distance between points. So you think of a space as anywhere where you can say two things are close or two things are far apart. And when I always say anything where you can do that, I really mean anything. I want you to sort of free your mind about what it means for something to be a space. So maybe you might have heard stuff about string theory and how there's extra dimensions, and maybe that's a picture of something like that. But what maybe you should think of instead that sort of is where these things become more useful is something like in a chemical reaction, you might have 10 different numbers measuring of how many of the amount of various components you have. And if two numbers, your longitude and latitude, can tell you where you are on Earth, and three numbers can tell you, your precise location in this room, including height, then 10 numbers are specifying where you are in a 10-dimensional space. And that's where you start to get to medium-dimensional spaces, let's call them. Because 10 is not a very big number. But if we imagine the weather space, which is the weather on all of planet Earth, is 1 point, on 2 different days, you might say the weather was similar, and on 2 different days, you may say the weather is different. And if you can say 2 points are similar and different, you've got a space. But how big is this space? Well, how many numbers does it take to specify the weather on the entire Earth? Maybe 1 million, maybe 1 billion, maybe 1 trillion. And that's where we really get to high-dimensional spaces, things that are billions and billions of dimensions. And that's where we really have to start going way, way beyond our intuition when we think about donuts and donuts with 2 holes and spheres. Okay, but in order to talk about spaces, you sort of need to know how to build them, how to construct spaces. I mean, if we're going to study these things, we need to build them first and then study them. We can't just study them and then figure it out later. And a standard way to do this is to sort of build them out of pieces. So with a sphere, you might imagine poking a hole at the top and then unwrapping it to get a plane. And so you can say that a sphere is built by taking one plane, wrapping it, and then adding 1 extra point. So you might say a sphere can be constructed from a 0-dimensional cell, that point at the top, and a 2-dimensional cell, which is the rest of it. And so you can attach those two, and those are the 2 building blocks you needed to build a sphere. So you could say a sphere is given by 1 point plus 1 plane. And for this torus, or donut, you can build it from 1 point, where those 2 marked circles intersect. Then you add on those 2 marked circles. So you've added 2 lines to make those 2 circles. And then you add 1 plane that you wrap around the 2 of them to make the whole thing. And so again, you're seeing that spaces are built out of pieces, and I'm going to call those pieces cells. And so a 1-dimensional cell is like a line, a 2-dimensional cell is like a little plane, a 0-dimensional cell is a point, and a 3-dimensional space cell is something bigger. So let's look at a slightly more complicated space. This is a kind of funny-looking space. If I'm in over here in this space and I want to get to there, then I've got to go up and around here, and the dimension isn't constant. Some places it looks 3-dimensional, and some places it looks 0-dimensional, and up there it looks 2-dimensional. And so this is an example of a space that has 18 0D cells, each of these points. It has 23 1-dimensional cells joining all of those things together. It's got 8 2-dimensional cells, each of the triangles, and it has 1 3D cell, the interior of this tetrahedron. And maybe what this space will convince you of with its sort of seemingly random structure is that spaces with many cells can be very complicated, and it's hard to navigate in them. So we do here what mathematicians always do when you encounter a really hard problem. You don't work on it. You say, oh, that's too hard. You go to something much simpler. So what I'm going to focus on are 3-cell spaces. Now, before we get to 3-cell spaces, we should do 0-cell spaces and 0 cells, 1-cell spaces and 2-cell spaces. So when you're building a space, you probably always start with a point. You have to have something, so you start with a point, and then you're going to start building from there. So those will be our 1-cell spaces, are just the point. And then there's this amazing fact that when you add a second cell onto a point, it always builds an n-dimensional sphere. So if you add a plane to a point, it'll make a 2-sphere, like what we live on the Earth. If you add a line onto a point, it just always makes a circle. And if you add a 3-space onto a point, you make a 3-sphere, which you're maybe not used to thinking of, but it's like the whole of space with one extra point at infinity. And that sort of ties everything up nicely. So if said differently, we just know what the 2-cell spaces are, and they're all spheres of various dimensions. So every 2-cell space is a sphere. OK, so now 3-cell spaces. And this is where suddenly things explode. And I think a lot about 3-cell spaces. They'll have one 0-dimensional cell, one n-dimensional cell, and one m-dimensional cell. Now, it turns out that there are many, many different 3-cell spaces, far more than there are spheres. And a question, like if I could get to answer one question, probably I'd ask, how many are there? You know, if I could just ask, you know, the powers that be, how many, you know, one question, this would be a good question for me to ask. I wouldn't want to get too ambitious. So, how many? So it turns out that the difference of k and m is really the main thing that matters here. So for the rest of this talk, I'm just going to focus on k and how many of these things there are as a function of k. And here's the small values. So this has been hard-won computation of, you know, decades and decades of mathematical research to learn that this number goes infinity 2, 2, 24, 1, 1, 2, 240. Now, these numbers just look essentially random, and that's the beginning of what this looks like. It takes a lot of work to determine how many of these 3-cell spaces there are, and then we just don't really see patterns in the data after that. OK, so this goes up to dimension 8, and this probably represents the first 40 years of work in my field. And I'm going to go to a visual representation of this now. The 2 1s correspond to the fact that you see nothing in this graph. I could give a 2-hour-long lecture in just how to interpret all the data in these graphs. What you're supposed to take away here is that the columns mean the values of k, and that it looks kind of simple here. And then when we zoom out for another 30 years of progress, it starts to look more complicated, and things are getting worse. And here this is up through dimensions about 30. And then here's the current state of the art through about dimension 100. So what you can see here is that the number of 3-cell spaces, as the dimension goes towards 100, it goes from something you could reasonably memorize to something you simply couldn't. I mean, OK, maybe you could memorize this with a lot of time, but it gets to be an absolute mess. But the thing is about high-dimensional spaces, you know, when you think about dimension 100, that sounds like a lot. But when you think about numbers, 100 is not very big. Like if I go out to dinner, and at the end of dinner I'm supposed to pay, and it's 100 kroner, or less than 100 kroner, I'll think, oh yeah, if this was a good meal, I'm definitely coming back here. Because 100 is not a big number. But, so, we need to go to much, much larger numbers to like really probe truly high-dimensional spaces. But this diagram here, it's reached the point where it's at the human limit. This is the limit of what humans can do by hand, just proving theorems. And if you want to go way, way beyond this and ask questions like, does the number of 3-cell spaces go to infinity as the dimension goes to infinity? You need a totally different approach. So what I'm working on right now is trying to say, OK, this is the human limit, but what's the computer limit? But the computer limit might be a diagram twice this size or 3 times this size. But if you really want to go to all the way to infinity, you need a totally different approach. And so this is where we come to the idea of periodic families. So the idea of periodic families is that if you look at this function that is the number of 3-cell spaces as a function of the dimension, or a function of this parameter k, then you could try taking the Fourier transform of this. And this sounds completely meaningless, right? You're looking at decomposing some function where the input has a meaning, it's the dimension, in terms of periodic waves. But the idea is if you can make sense of it, then it allows us to probe incredibly high dimensions because you have this periodic wave and you're decomposing a function as a sum of waves. And every time you get a peak in that wave, then you're going to get a new interesting space, and you'll get those spaces in dimensions as high as you want. So the primary technique for probing arbitrarily high dimensions has been constructing families that mimic these waves and thinking about the Fourier transform of this function. And this road and this way of thinking is what's called chromatic homotopy theory. And the sort of triumph of chromatic homotopy theory is that Adams, Barrett, Toda, Mohwald in the 60s and 70s determined all the periodic families that have period. So period is, here is how often a phenomenon repeats, 2, 8, 4, 2, 4, 8, 10, 12, 18, and 20. So I have a favorite one of these. It starts in the difference k being 2, and it's 8 periodic, so it's a phenomenon that occurs with 2, and then in dimension 10, and then 18, and so on. And that is really something that goes to infinity, and we can sort of see the geometry of these things being closely related to each other. But you might look at these numbers up to 20 and say there's a couple missing. And so now the periodic families always do have even period, so the missing numbers are really here 6, 14, and 16. And the other thing that's notable here, and this is really why this perspective works, is there's a sort of feature that these periodic families, they'll begin in some dimension and then they repeat after that. But so far, at least in these cases, there are only finitely many families. And this really made this a reasonable way to study things because we had this big problem, and then you broke it up into pieces, and there's one piece for each period, and then with a finite amount of work, you can figure out what happened. And then that was where things stood for a very long time, and people kept trying to figure out what happens in the case of 6, because that's the next number. And they really just didn't make progress. And then about a year ago, or 2 years ago now, me and my co-authors first figured out how to sort of really understand period 6, or rather how to not understand it. What we did was we found a way to construct infinitely many periodic families, and sort of what you might think of this as some sort of resonant catastrophe. You have some sort of wave of period 6, and it starts here and it gets just louder and louder as the dimension goes up. And so with this sort of catastrophe that happens at 6, 14, and 16, because of this resonance, what you find is that the amplitude just goes to infinity fairly rapidly. So we do learn that the number of 3-cell spaces grows quite rapidly with the dimension. But unfortunately, the price we pay is that our only technique for studying these things can never fully answer what happens. Because with this sort of resonance, it breaks down, and the whole chromatic approach actually cannot answer all the questions. So this is, I guess, the end of the road for chromatic homotopy theory. All right. Thank you.